Hi, Math 1 honor students. This is going to be one of your independent study assignments for this lesson right here, functions, notes on relations and functions. So here we go. So you need to take the notes that were handed out in class after the test. If you weren't there, then you should be able to find them in the materials file in Jupyter Grades. So as we go along with this, be filling in your notes here, and when you need to, just go ahead and pause it so you can fill these in. But we're going to talk about relations versus functions today. So every function is a relation, but not every relation is a function. So what makes a relation is it's just a pairing of input and output values. So you don't have a relation if you only have, say, an x value but no y value to it. So it needs to be ordered pairs, because we're going to be talking about graphing also today. And so on the coordinate plane, you need to have inputs and outputs, right? So you can't have a list of inputs without any output and vice versa. So there's got to be an input and an output for each one of those. The domain are just all your inputs. They're your x values. They are the independent variable. Okay, and when we list the domain, you always want to write them from least to greatest. And you don't repeat any values. So if you have the same x coordinate out of your ordered pairs, you're only going to list it once. The range are just your output values. They're your y values. They're the dependent variable. And again, we will write them from least to greatest. We won't repeat any values. So if we have a y value repeated from our input-output pairs, our ordered pairs, maybe they're given to us in a table, maybe they're given to us in a graph and we're just looking at them, okay? But however, they're given to us, and when we go to write out the range, we're just going to write them from least to greatest, and we're not going to repeat any values. And so what makes a relation a function is that every x value has only one y value. Each input has only one output. Okay, so I said this earlier. Every function is a relation, but every relation is not necessarily a function. So with this list of ordered pairs, we want to identify the domain and the range of this given relation. Then we're going to represent this relation using a mapping diagram and answer the question, is the relation a function, and explain our answer. So for the domain, we want to look at all of our x values. We've got 5, -3, 3, and -1. And we want to list them in order from least to greatest. So we've got -3, and then -1, and then our 3 and our 5. So we would list them like this. And sometimes you'll see me or other people, or maybe even your textbook, put this list into braces. That's just set notation, so that's common. Now let's look at the range. Remember, the range are the outputs. So we've got -2, -4, 3, and -1. We'll list them from least to greatest and not repeat any values that may have been repeated in the list, and it doesn't look like any of these have. So we've got -4, -2, -1, and 3. So is this relation a function? Let's, before we answer the question yes or no, it's nice to put our domain and our range values like this, ordered, and then draw arrows. This is called mapping diagram. So this -3 went with the -4. This -1 went with the -1. You can see from the ordered pairs up there. This 3 right here went to the 3, and the 5 was with the -2. So we would say this is a function because each x value has only one y value. You can see very nicely from this visual that you've got only one arrow coming out from each one of your domain values. It's not going, one of these is not going to two different y values or two different range values. So that also is an indication that you've got a function because there's only one arrow coming out of each one of these domain values. So do you see how to do this? Why don't you pause the video and answer the rest of the questions from number 1. You've got different parts there. And then unpause this and see if you are correct. So I am going to assume now that you have paused the video and you have done your own work, and let's see if you have the correct answer here. For this, we have a domain of -5 and -1 and 3 and 4, and our range here, you can see how we have a -5 twice. We only list it once. And we've got a -2 and we've got a 4. So when we list them like this in our mapping diagram, you can see that we still have a function. Even though two different x values went to this y value, that's not what determines if a relation is a function or not. It's if each input has only one output, if each domain x value has only one y value or range. So yes, this is a function because each input has only one output. For part C, we've got -4 and we've got 4 listed twice, so we're going to only list it once here. We've got 4 of them in there. We've got a 5, and here for the range we've got a -2 and a 1 and a 2 and a 5. So again, with your mapping diagrams, now right there you see how you have 2 arrows coming out of this 4. This input has more than one output. It has 2 outputs, so it is not a function. 4 has 2 y values. There's different ways you can write your explanation. You could say each input does not have only one output, or one of the inputs has more than one output, or you can be specific like this. Now you're given a table of values. So this is kind of nice and convenient. They've already got them ordered for you from least to greatest. And now look at all of these. They're all the same y value. But that's okay, because look at what's going to happen here. They're just all going to that -4. But each input has only one output. So later on in another math class, you will study functions called one-to-one functions. One-to-one functions are such that not only does each input have only one output, but each output has only one input. So this is a function, but it's not a one-to-one function. So don't forget to write your reasoning. And then we have this example. Every input is a 1, and the range looks like we've got 1 and 2 and 4 and 7. So here, this one definitely has more than one output, doesn't it? So it is not a function. Each input does not have only one output. Okay, let's see what you have for this one. Again, nicely ordered for us. For the domain anyway. So when we do our mapping diagram, let's see if we have only one arrow coming out of each x value, and it looks like we do. Yes, this is a function. Each input has only one output. Okay, so some more notation. So function notation, this is very important. This can be treated like your y value. Say you had an equation, maybe it was in slope-intercept form. You could replace the y with this new function notation called f of x. Sometimes people say f of x, sometimes they say f at x. It never, ever, ever means f times x. This is simply a notation device. These parentheses do not mean multiply. It means we're going to call this function f, and whatever variable we have inside the parentheses, that is going to be the variable that we will see in the equation on the other side of the equal sign. So in this function notation, if we have a variable at all, it could be a constant function, that's okay. But if there is a variable, it should have that variable, whatever is listed right there in the parentheses. And so it means the value of our function when x is our input. So here's an example. If you're asked to find the value of a function for some given x value, or maybe more than one, this means you plug in the given x value and you solve for f of x. You want to plug it into, like you're going to see some examples where they're going to ask you to find, say, the value of f at 2. It means you're going to plug in 2 everywhere you see an x, and you're going to follow the order of operations and evaluate that expression on that side of the equal sign. And that would be the value of the function for that particular given input or x value. if you're given the value of the function, they're telling you what f of x equals, and you're asked to find the input, the value of x, you would replace f of x with the given value and just solve for x. So we're going to have some of these examples coming up here. So go ahead and pause this video and write down anything that you haven't finished writing down already on your own notes, and then unpause it and continue when you're ready. So when we are given graphs, there's this very cool thing called the vertical line test, which we can use to determine if the graph is actually showing us a function. Okay, so given any vertical line, if you can imagine it, or you could put your pencil or your finger or whatever and move it across the graph going from left to right. If that graph crosses the graph only once in every place, it is a function. If it crosses the graph more than once, it is not a function. So this is an example. We've got a parabola here. They're showing you this vertical line. If it started over here and moved all the way across, it hits the parabola in only one place at every point along the curve of this parabola. This is a function. This would not be a function because look, as soon as you move off of this vertex right here, you would hit the parabola in two places everywhere. And as soon as it hits your graph anywhere more than once, boom, you know you've got something that is not a function. It's just a relation. So your reasoning for why you would say something is a function or is not, you could say, yes, it's a function, it passes the vertical line test. Or no, it's not a function, it fails the vertical line test. So let's go with these examples of evaluating our functions. So here's one of our examples where we're saying f of x equals negative 4 minus 2x. That's like saying y equals negative 4 minus 2x, or y equals negative 2x minus 4 if you wanted to put it in slope-intercept form. But what they're telling you to do is they're calling the function f. Here's the variable x. You can see there's a variable right there. They want you to plug in negative 1 for x. Look at, they've taken this x out and they put a negative 1 in it. So that's what they want you to do. They're saying, tell me what this equals if you plug in a negative 1 where the x was. So you go ahead and just evaluate this. Negative 2 times negative 1 is positive 2. And positive 2 plus that negative 4 is a negative 2. So you could say f at negative 1 equals negative 2. The value of the function when our input is negative 1 is negative 2. Here's our output for this input. We would have the ordered pair negative 1, negative 2 somewhere on the graph of this line, right? Okay. So here we've got a quadratic. Now look at, we've got the letter G here. There's lots of different letters we can use. Sometimes they correspond to the context of the problem, like say for instance the height of an object after t seconds. We would say that would be the function h of t. Okay, so excuse me, there's lots of different variables we can use, but we want you to evaluate this one when x is 0. So if you plug in 0 and square it and then subtract 1, you just get negative 1, right? So g at 0 equals negative 1. Now go ahead and if you have other examples, work those out and then unpause the video and see if you are correct. Wait, I guess you don't. I'm going to stop this for a second